Euclidean spaces. For each positive integer k, let Rk be the set of all k tuples of the form where x sub 1, x sub 2, all the way up to x sub k are real numbers called the coordinates of x, also called the components of x. The elements of Rk are called points or vectors, especially when k is greater than 1. If y is a vector with coordinates y sub 1, comma, y sub 2, comma, all the way up to y sub k, and alpha is a real number, we define x plus y as this vector, whose first component, x1 plus y1, is simply obtained by adding the first components of the vectors x and y. Similarly, the second component of the vector x plus y is obtained by adding the second components of the vectors x and y, and so on. And the scalar multiple of the vector x, alpha x, is simply obtained by multiplying every component of the vector x by the real number alpha, so that the vectors x plus y and alpha x are in Rk. For example, if x is a vector with coordinates -2, 2, 0, 1 from R4 space, and y is a vector with coordinates as shown from R4 space, then the sum is a vector with coordinates -1, 1, 2, 5. For example, the fourth coordinate of the sum is obtained by adding the fourth coordinates of the vectors x and y. Similarly, the vector 3x is obtained by multiplying every component of the vector x by the scalar 3. This defines the vector addition and scalar multiplication. Of vectors in Rk, and make Rk a vector space over the field R. The zero element of Rk is the zero vector, written in boldface 0, whose all components are zeros. We also define so-called dot product, also known as inner product or scalar product of vectors x and y, which is denoted by this symbol x dot y, and defined to be equal to the sum of the products of the corresponding components, which can also be written by using the sigma symbol. And the norm or length of the vector x is denoted by this double bars symbol, and is defined to be equal to the positive square root of the dot product of the vector x with itself, which can also be obtained by taking the square root of the quantity, the sum of the squares of the components or coordinates of the vector x. For example, if x is a vector whose coordinates as shown, and y is a vector whose coordinates as shown, then the dot product of the vector is obtained by adding the products of the corresponding components, which is simply 0. And the norm of the vector x is the positive square root of the sum of the squares of the coordinates of the vector x, which is positive square root of 9, which is simply 3. A vector space Rk together with the above defined inner product and norm, this is a mathematical structure called Euclidean K space. Theorem. Suppose x is a vector in Rk space and alpha is some real number, then the following statements hold true. A. The norm of a vector x is non-negative. Statement B. The norm of a vector x is equal to 0 if and only if the vector x is the zero vector. Statement C. The norm of the vector alpha x is equal to the product of the absolute value of alpha and the norm of the vector x. Statement D. The absolute value of the dot product of the vectors x and y is smaller or equal to the product of the norms of the vectors x and y. Statement E. The norm of the vector x plus y is smaller or equal to the sum of the norms of the vectors x and y. Statement F. The norm of the vector x minus y is smaller or equal to the norm of the vector x minus z plus the norm of the vector z minus y. The inequality in statement D is famously known as Cauchy-Schwarz inequality, also known as Cauchy-Bunyakovsky-Schwarz inequality. The French mathematician Cauchy lived in 1789 to 1857, who first published this result in 1821. Bunyakovsky, the Russian mathematician, who lived in 1804 to 1889, published the result for the integrals. The German mathematician Hermann Emendas Schwarz rediscovered the result in 1888. This is a useful inequality encountered in many different settings, such as linear algebra, analysis, probability theory, vector algebra, functional analysis, and other areas of mathematics. It is considered to be one of the most important inequalities in all of mathematics. The inequality in statement E is known as the triangle inequality. If we take a vector x in R2 space or R3 space and another vector y in the same space, then the sum of the vectors x and y can be obtained by the triangle law of addition of vectors. Then the length of this side, which is obtained by the norm of the vector x plus y, is smaller or equal to the sum of the lengths of the vectors x and y. The inequality in statement F is called the reverse triangle inequality. Let's try to prove some of these statements. The proof of the statements A and B are obvious. They just follow from the definition of a norm of a vector. Please try to prove these statements. We now turn into the proof of the statement C. Let's have a vector alpha x with coordinates alpha x1, alpha x2, all the way up to alpha x sub k. Then its norm is given by this expression, which is the positive square root of the sum of the squares of the components of the vector alpha x. Now if we square the factors alpha and x sub k and we split alpha squared, then we get this expression. Now we distribute the square root over the factors, namely alpha squared and the sum of the xi squared. We get this expression. The first factor is by definition the absolute value of alpha, and the second factor is by definition the norm of the vector x. This concludes the proof.